Hello and welcome. In this video, we'll talk about how to access pybamm database options, what are the options available, what are the different literature sets available, and then this can be very useful at early stage when you don't have access to all the relevant parameters to create a DFN model. And one way is to do literature review, but pybamm has its own database of the most relevant literatures, which has the relevant parameters required to model a DFN model. So that can be used to not just model DFN but also SPME, SPM, ECM, sodium ion, and so on. So we'll look at what are the parameter database options, how to include them in the model and solve. Then what are the parameter values in the hindsight, and finally how to update the parameters as needed for calibration. So let's begin. The first step would be to import pybamm and then loop through. So we'll do import pybamm and we'll create a for loop for name in pybamm.ParameterSets dot keys. So think of it as a dictionary which has a variable called name or a key called name. The name corresponds to the name of the paper from which the parameter set was derived. And then it has a bunch of different keys which correspond to parameter names, chemistry, and so on. So firstly, let's print out what are the names of papers available, and then from there on we can further deep dive into what's inside. So first step is for name in pybamm.ParameterSets.keys. We would like to just print out the name. So this gives us a list of all the available options as of now. And then next question would be, okay, we now have the list, but which one is suitable for our needs, and what chemistry or what battery technology does it represent? What kind of battery is it? So to first find out the type of battery, chemistry, we need to identify what are the keys of this dictionary. Each of these is a dictionary in the background. So for that, we can simply do print pybamm dot parameter sets and then pass on the name. So this gives an extensive list of keys and their values. So chemistry for the first one, for example, is lithium ion, the second one is sodium ion, and so on. But it doesn't clearly mention, okay, within lithium ion, what's the anode and cathode like, right? And this list is huge, so it's hard to go through each and every entry of this. So definitely a second level of filtering is required. So for that, what we can simply do is create a one-liner print statement which can print, for example, again, chemistry is one of the keys which is clearly visible from here. If you would like to print the value of chemistry along with the name, the syntax goes like this. So you can do a F string. This will basically help you combine the strings and variables. So we'll pass on the name and then we would like to print in open curly brackets. We would like to pass on chemistry now. and we can simply hide the first two. So this way we now get a relatively cleaner list, which now gives us for each of the paper what is the chemistry. Now let's look at what the anode and cathode correspond for each of these. For that, we can add another print statement and call out. We can copy the same. We just need to change what's passed in as a key. Instead of chemistry, we will replace it with negative electrode OCP. You can simply type in here negative electrode OCP. And now because OCPs are generally a function and not a constant value, so OCPs, which is a function of, let's say, the stoic of the given electrode, and the negative electrode in this case is for the first one graphite, for the second one HC, for the third one graphite again. The fourth one is composite, which doesn't have a negative electrode, so it eventually failed. We can do the same for positive electrode as well and find out what each of these represent. So first is LCO, then the third one is NMC, the fourth one is also NMC, but it's a composite and it doesn't have a negative one. The fifth one is ECM, so it doesn't have, it's neither have a positive nor a negative, because it will have maps for OCVIR, R0, RC maps. So this way you can further deep dive into what's inside. So let's come back to the original extensive list. Now, when you do this exercise, you'll find out that Chen 2020 is basically a lithium ion cell. And by the way, to overcome those errors, you can also do a try except loop, which you can easily get through wipe coding. And you can combine it with this for loop to print out eventually all these combinations and append to this list the respective anode cathode. In cases where we are working with half cells or composites, we might not have anode or cathode in those scenarios, so an ECM. So in that cases, you can use try except to print NA where it's not there, uh, and that will fix things up. So once now let's move ahead with Chain 2020 as we identify its NMC with graphite. So we'll go ahead with sorry, this one. And for that, let's now understand how to include these parameters in a DFN model. So we can do DFN equals to pybamm.lithium ion.dfn. This way we have created a DFN model. Now, the usual way of doing it was we do a simulation, pybamm.Simulation. So when we add a simulation to this, it will basically ask for some uh, parameters within it or at arguments. And so first argument is DFN. The second argument would be the parameter values. Now, if you don't pass the parameter value, it will choose the default ones. And then we do sol equals to sim.solve. And then finally sol.plot. So before adding the parameter set, I would like to show what the base parameter is. Now it failed because we didn't define an experiment. How to define an experiment is covered in the previous video. I'll skip that for now. For this one, since there's no termination condition, If we define experiment, it also consists of the termination condition. But here, since we didn't, it will run a discharge at 1C, but where to stop is not clear, so we need to pass on a time argument additionally, and then it should fix things up. So with this, it uses the default parameter set in pybamm, and let's see what current voltage or current it operates at, which would correspond to 1C. So you can see the plots now, and it's all at roughly 0.7 ampere, which seems to be the capacity of the default cell, and the voltage curve is shown here. Now let's add a parameter set gen 2020. For that, we can just do parameter equals to pybamm.ParameterValues, and then it takes the argument of the parameter name itself. We just need to pass on this gen 2020 as a string. And additionally, within simulation, it also accepts parameter values. So we just need to copy this here and then assign parameter to the parameter values. So this way, instead of using the default dataset, it will now use Gen 2020 dataset, which has a capacity of 5 ampere hour. So now if we rerun this, we can see that the current is 5 amps, which is 1C, and the voltage starts from roughly 4.2 all the way to 2.5. So this is NCM graphite combination. Now we can also try out Prada, which is LFP, and see how the shape changes. So you can see now the value of capacity goes down to 2.3, and the voltage curve is much more flatter because it's LFP now instead of NMC. So this is how you extract the parameters set values and run a model. Now let's see what are the values in the background for each of these parameters. So for that, we can simply do this. Can copy this and then print this out. So we can clearly see here, this is an extensive list again. If you look at the positive electrode OCP, it says graphite here. For a negative electrode, it says LFP. It's LFP graphite combination. It has a lower cutoff voltage, upper cutoff voltage of 3.6, lower cutoff voltage of 2 volts, and a capacity which would be nominal capacity 2.3 amps. And by default, the current function is 2.3. So now let's update this. We can update any of these parameters. And in the next section, let's see how to update current, for instance. So to do that, we can simply do param, which stores this Prada 2013, which is a LFP cell parameter set. We would like to now update it, which we can open curly brackets, enter, and then type in the string which you want to update. This is the key, and then the value of it you can assign whatever you would like to. So by default it was 2.3. Now we would like to assign 1 amp and run the model again. So let's copy the Quote from here, the last 3 lines. And if we rerun now, you can see it now operates at 1 amp instead of 2.3 amps, which was the default value. Similarly, you can also update the remaining parameter set, which would be useful for calibration process. So hope this was helpful, and see you in the next one.